Welcome to this tutorial on using the PIAAC international databases. In this tutorial, we will discuss sampling and assessment design and implications for analysis. Some of the challenges in large-scale assessments like PIAAC is that there are several domains, in the case of PIAAC numeracy, literacy, and problem-solving in technology research environments. The domains are very broad. There's limited testing time, physical and psychological, meaning we can only interview adults for so long before fatigue sets in. And there are challenges that we need to administer the items in a sensible design, we need to summarize the performance on those items, and we need to account for the unreliability of the estimates. In surveys like PIAAC, we resort to sampling. Sampling helps because it is impossible to test everyone on everything. There's too many people, too many items, and it would be too expensive to test all the people with all the items. But doing this is not necessary, and here we'll give two examples. One, the blood sample, which is when your doctor wants to know the state of your blood. The doctor doesn't have to draw all your blood. The doctor can draw a little bit of your blood, and from that sample of your blood can do the corresponding test. Regardless of where the blood is drawn from, given that it's so homogeneous, it doesn't really matter. And also, regardless of your size, weight, age, the same amount of blood will do. Then we also have the soup example, and imagine a soup that has multiple ingredients. It has the broth, and it has meats, and it has vegetables. To know whether the soup is ready, what we have to do is not eat all the soup, but we have to make sure that we stir the soup and taste the different components that make up the soup to make sure that they're all ready to be eaten. So in the same way, some people are tested on some of the things, and that's how these studies go. However, the results should be seen in the context of the person and item sample design. So how does sampling help? We select a few people from the entire population, and to those selected, we give a selected set of items. This is known as multiple matrix sampling, meaning some of the items are selected for some of the people. The selection of people is done by using a multi-stage stratified cluster sample design. Multi-stage in the sense that there are different stages of selection. Could be municipalities, blocks, household, person. It's stratified in the sense that the selection takes place across different segments of the population. This coverage of the different segments could be done explicitly or implicitly, and it is achieved by either systematic selection across a sorted list of individuals or targeted selection within different groups. It is a cluster sample because multiple individuals are selected from within segments of the population. Imagine a block or neighborhood, and from that neighborhood several individuals would be selected. The selection within each country varies, and this will depend on the availability of information and also cost reduction techniques that would be applied in each country. We also want to ensure representation of the different target population groups. We want to achieve desired precision levels for target reporting groups, and we want to build some level of redundancy in the sample so that we do not waste the time of an interviewer heading to a neighborhood and not finding the person that they were supposed to interview. The consequences of implementing the sample design is that we do not have a simple random selection of people from the population. Think of what happens when we select clusters and then persons within the clusters. The persons within a cluster are likely to be more similar to each other than to persons in other clusters. And this matters when we compute sampling errors. We'll show you in the next slide what happens. In this slide, we have the same picture in three different ways. We have one where we've done a simple random selection of pixels, that's the one on the left. Then the middle one, where we've selected clusters or blocks of pixels. And then the one to the right, where we have selected also blocks of pixels, but we've done systematic selection across the picture. And you'll see that the one on the right gives us a pretty good picture, better than the one in the middle, by systematically making sure that we cover the entire picture. We could also do something called oversampling, and in this picture you'll see how we decided to oversample or select more pixels from a particular area of interest, but notice that selecting those pixels does not distort or overtake what happens in the rest of the picture. Because of the way the individuals are selected to participate, they end up being selected with different probabilities. Sampling weights are the inverse of the probability of selection for a person. So, for example, if I select 2 out of 20 people, the probability of selection is 2 out of 20, or 1 over 10. The sampling weights will be the inverse of that, or 10, meaning now I have 2 people, each representing 10, which gives me back the 20 people that I selected those people from. So the weights tell us how much should each unit contribute towards the population estimates. Therefore, they can be scaled up or down as long as all of them are rescaled by the same factor. In other words, when person A has 4 marbles and B has 8 marbles, this is equivalent to A having 40 marbles and B having 80 marbles. B having twice as many marbles as A, or contributing twice as much as A. Sampling weights take into account the characteristics of the sample and selection procedures: stratification, adjustments for non-response, post-stratification, etc. The consequence is that sampling weights must be used always to get the correct population estimate. Now, sampling automatically results in some uncertainty. This is called error or variance. Which factors can influence the magnitude of the variance in a sample? How we select the people, how we sample, the sample size, and the variability within the population between and within the clusters. Think of a simple random sample and how these factors influence the variance of an estimate. Because we cannot sample from the population over and over again, we use replicate samples to estimate the sampling variance. By replicates, we mean that we systematically delete subsamples from the full sample to form replicate samples. We adjust the weights of the remaining units to account for the deleted units, and new weights are called replicate weights. We then produce an estimate using the full sample weight and an estimate from each set of replicate weights. And we calculate the variance of the replicate estimates from the full sample estimate. There are several replication procedures that can be used. We have the jackknife repeated replication and 2 variants, jackknife 1 and jackknife 2, and variance repeated replication with a phase variant. In PIAAC, currently, we use only jackknife 1 and jackknife 2. In this table, we see how the replication on the jackknife 2 works. Here we have the different clusters within different strata, and then for the overall estimates, we multiply the sampling weight by a factor of 1. And then for the first replicate, we multiply the weights for the individuals in this cluster by 0, and then the weight for the individuals in this cluster by 2, and we leave everybody else at 1. And then we calculate with this replicate, and then we move towards the right. Notice that once you get to the second replicate, the first 2 clusters go back to a factor of 1, and the next pair then gets a 0, 2. Notice also that this assignment of 0, 2 is random, so it's not always the same. Once we've done that, then we accumulate the square differences between the estimates using the entire sample and the replicate samples, and we multiply it by a factor f, which is going to vary depending on which replication method we have used. Note that the method and number of replicates are country-specific. Table 15.6 in the technical report will indicate which variance replication method goes with which country. When it comes to the PIAAC assessment design, note that not everyone takes everything. The path taken is dependent on the person's skills, and no task is given to a representative sample of the entire population. Therefore, we need to put everyone on the same scale, despite having taken different sets of items, and we need to compute the uncertainty due to the reduced and set of items taken. In this graphic, you see the PIAAC assessment design, And you know that depending on the person's ability, they could get routed to take the assessment on computer, and depending on a random selection, they will end up taking literacy, numeracy, problem solving, or some combination of those domains. To be able to compute comparable scores, regardless of the set of items that the student in order to be able to compute comparable scores, regardless of the set of items that the adult responded to, we resort to item response theory. Item response theory is based on the assumption that the response to an item depends on the interaction between the ability of the respondent and the characteristics of the items. In other words, an item is difficult to the extent that a person is not able to respond to the item, and a person is able to the extent that they can answer correctly difficult questions. Item response theory allows us to summarize data across multiple items, even when different people take different sets of items, and it facilitates linking when dealing with multiple test forms, as we have in PIAAC. In these slides, what we want to highlight is several of the issues faced with measurement. We have two instruments in this case, a high bar, an easier high bar, and a more difficult high bar. And depending on the size of the person, we could choose to ask them to jump one or the other. But even when we have already selected a high bar for the person to jump, notice that our measurement goes in 10-unit increments. So if somebody clears 60, 70, and then fails 80, 90, and 100, and the question is, how high can this person jump? All we are able to say is that they can jump 70, but they cannot jump 80. Now, if we compare that person with this person, we can and we observe the same performance where they both jump 60 and 70, but not 80. We could also say that chances are that this person would not be able to jump as high as that person, and therefore we could build a probability distribution of likely outcomes along this continuum. So in the case of the high jump, we're looking to see what is the highest height that an individual can jump. In the case of IRT, we're looking to see which is the height that an individual can clear half the times that that person attempts to clear that height. Under IRT assumptions, persons of high ability are expected to answer easy items correctly. Persons of low ability are expected not to answer difficult items correctly. The probability of a correct answer depends on the item parameters and the ability of an examinee. There are no assumptions made about the distribution of skills being normal, but there is an assumption made that there's a single dimension that explains the responses to the items. As part of the scaling procedure, plausible values are used. Plausible values are random draws of the estimated ability distribution of adults with similar item response patterns and background characteristics. Think of a regression where the predictors are item responses and background data. Plausible values are optimal for obtaining population estimates. They should not be used for individual reporting. When using plausible values, you will need to compute each statistic with each plausible value and average the results, and then compute the variance due to the imputation. Furthermore, when using plausible values, never treat them as an individual score, never use the average, always repeat the analysis separately with each plausible value when selecting variables and when selecting people, and report the average of the statistics computed across the 10 plausible values. When conducting significance testing, combine the measurement variance with the sampling variance. Here we have an example of different results when using two plausible values. In this case, the first and the second for literacy. You'll see that while most here we have an example of what happens when we use two different plausible values. Here you will see that we're using the first and the second plausible value in literacy. And notice how, while most cases are classified in the same achievement level or performance group, many people are still not classified in the same. Their classification will vary depending on which plausible value you use. This is a feature of the plausible values that highlights the unreliability of the measurement that we have, and it allows you to get an estimate of that unreliability. Having discussed how to calculate standard errors, we have the two formulas for cases when you are not using plausible values and when you're using plausible values for your analysis. Here's one last point to summarize the calculation of sampling and imputation variance, which has to do with statistical significance. Statistical significance tells us if a particular difference is relatively large in relationship to an error or uncertainty expected by chance. Depending on our interests, priorities, and consequences of the decisions that would be made, the threshold to consider something large or small varies. We usually assume a normal distribution of the error. In short, the way this works is that if we select two samples from the same distribution, that would have the same expected mean, we would expect the differences between those two samples to stay within a particular range. Now, if the difference is smaller than expected or larger than expected, we would say that the differences are statistically significant. The importance of calculating the proper measurement and sampling variance is that that calculation is going to give us the placement of these arrows in that theoretical distribution of expected differences. And as we see in this table, doing the right calculations matters. Here we have the results for females and males across 4 different countries. And then here we have the standard error assuming simple random sample. And this is the standard error taking into account the assessment and the sample design. And we see that the standard error assuming simple random sample is always smaller. And if we look at the differences between males and females, we see that if we assume simple random sample, that the error, the size of the error, is actually going to be bigger than if we take into account the dependencies of the sample. As a final note and in summary, if you do not take into account the sample and assessment designs in your analysis, chances are you will end up with the wrong answer. Programs like the IDB Analyzer and the Data Explorer presented in separate videos of this series take these into account. We recommend you using them. Thank you for watching. For more information or comments about these videos, please write to egonzalez@ets.org. Thank you.
This video was made possible by the Institute of Education Sciences of the U.S. Department of Education, through Grant R305B160020 to Educational Testing Service. The opinions expressed are those of the authors and do not represent views of the Institute or the U.S. Department of Education.